So we'll talk about basic rules of counting today. And I'm not going to derive many of these rules, just give you a very brief overview, and we will do a few of them, permutations and combinations. So let's see what are the rules of counting. First of all, we have to repeat what we mean by an experiment. An experiment is some action we perform and we have some observations. It results to some observations. It can be a game of luck. We cast a die, that's an experiment. We draw cards from a deck of cards, that's another experiment. Or we simply group people into groups, that's an experiment. Action we perform and observe outcomes, and observe its outcomes. So that's an experiment. Now, when we perform two experiments serially, the first one has n outcomes, the second one has m outcomes. After performing them one after the other, the combined experiment has n times m outcomes. So the combined experiment So a very good projector. Okay, so let's say that, let's see why this is true. Let's give an example. Suppose that experiment 1 is to pick coordinates on the x-axis, a discrete set of coordinates. Let's say 1, 2, 3, 4, 5 coordinates. 0, 0, and then that's the x-axis. And here on the y-axis, I pick 3 coordinates. That's experiment 2. Now, if the resulting grid is the combined outcome of the two experiments, and those points, each one of these points, has coordinates that come both from, one is the x coordinate comes from the set of x coordinates I have gathered, I have picked. The y coordinate comes from the set of the y coordinates I have determined. So how many points do I have? I have 3 times 5, 15 points. That's the grid, and this is exactly an illustration of what I mean. The combined experiment has n times m outcomes. Okay? Now, this is fairly easy to understand. And now let's try to understand. Let's try to apply this principle. So suppose that I have 3 symbols. And I would call these symbols 3 distinct symbols. They are different from each other. Okay? Like A, B, and C. How many words can I create with these 3 symbols? By words, I mean words that don't necessarily have a grammatical meaning in English. Don't have to follow any rules, like any rules of spelling, okay? Because if we have to follow any spelling rules, we cannot create a word like ABC. We can say BAC, but not ABC, because that doesn't correspond to a word. By words, I mean any way you can place these symbols. So what is exactly what I'm doing here? Those words are like what? Now think like a computer scientist. Those words have a meaning. It means it's very important which letter comes first, which comes second, which comes third. So how many words can I create? Okay. How do we find this? Important is not to know what the number is, because suppose I add one more letter. If I add a fourth letter, can you give me the answer so quickly? How do you find 24? Oh, you say 4 factorial. Okay, let's arrive at the result. 4 factorial or 3 factorial. Do we know how to arrive, first of all, at this result? Those who attended in the morning, actually in the afternoon, the early afternoon? Of course, no, the answer. Because I'm repeating myself. I did the same thing in the probability class earlier. So it's more polished. You're getting the more polished version of the earlier lecture. So let's see the mechanics. To understand the counting here, whether it's 24 or 6, if we had 3 symbols, let's understand the mechanics. I have position 1, position 2, position 3, position 4. The rule for interpreting the symbols is that which is on the left is the very first one. Okay? So if you have how many choices for the first one? You have 4 choices. So you have 4 choices for the first one. Now that choice is gone. You pick one. You cannot repeat. Let's say now that you cannot repeat those letters, because I told you I give you those 4 symbols. Use them. Okay. So I didn't tell you use them with repetitions. Like giving you four flags. Flag 1 has number A, has letter A on. The second has the letter B. The third flag has the letter C, and the fourth flag has the letter D. So you have only those 4 flags. That's the only thing you're being given. So I'm making the flags here. Those triangular flags. Do you know how we call these flags? The triangular flags? Those are called pennants. If you've been in the Boy Scouts, you would have known about the pennants. Or done sailing or something to that effect. So you have 4 pennants. So how many choices do you have? You're going to put them, let's say you're going to put them vertically. Make a symbol vertically. So the top position. How many choices do you have for the top position? 4. Obviously 4. Now you pick the second position, the one below. Right after. Right below. How many do you have? Now you have only 3, okay? And then, of course, for the third position from the top, you have 2. And finally, you're left with 1 pennant, so there's no question who's going to be here. 1. So you have 4 times 3 times 2 times 1. And how do we call this arrangement? It has a special name. It's a permutation. Now, this is a permutation. What I created is a permutation, and a permutation is an ordered selection So the order counts. The flags are important, which is on the top, which is one below the top, and so forth and so on. That's what we mean an ordered selection. But since I had 4 flags, 4 pennants only, I cannot use them more than once. I use them, as I say, I pick them without replacement. So it's an order selection without replacement of, as we say, n items, of k items out of n. Out of a pool of n distinct items. So that's a permutation. And in general, that permutation can be done in n factorial divided by n minus k factorial. Here, I used all the four. So k and n were equal to 4 in my example with the pennant. So n was equal to k is equal to 4. And therefore, the result was 4 factorial divided by 4 minus 4 factorial. What is 4 minus 4 equal to? 0. What's 3? Okay, usually it's 0. It's been for so many years, 4 minus 4. So what is 0 factorial? By convention, we say it's equal to 1, okay? So 0 factorial is equal to 1. That actually gave you the well-known 4 factorial. So the rule I'm giving you here is an extension of the rule you've learned in finite math. Okay? Any questions? No questions. Now, combination. What is a combination? A combination is an unordered selection of k items, let's say without replacement, of k items out of n. And when we do this, we have n choose k choices. This can be done in n choose k ways, which is n factorial divided by k factorial divided by n minus k factorial. So the difference between combinations and permutations is that we have one, permutations are ordered, combinations are not ordered. Let's see an example, a typical example of a combination. A typical example of a combination is a deck of cards. It is a hand of cards. That's an example. Where for a permutation, I just gave you one. The pennants. Place the pennants in an order where the top one is the first one to read. And the order goes vertically. Any questions? Okay, both are without replacement.
So, in permutation case, if you get k equals 0, which means that
You select no items. You can't select no items, then if you select nothing, then we have no case to discuss. Okay, so at least k has to be greater than or equal than 1. You have to select at least one item to make a selection. You can't select 0 items. You don't do any work. How? There's no way to select, yes. Select means I do something. And
k means when I select out of the group.
you select out of a group, yes. But the group, you have to be careful about the group. The group contains distinct items. Items that you can distinguish from one another. Like a deck of cards can be a group. We cast a die with so many sides. Each side has one number, and no two sides have the same number. So those numbers are distinct outcomes, distinct elements in the group. Okay? Yes? Yeah, but you don't.
I'm saying, so
Yeah, it's still, yeah, it doesn't make it. Technically, it's correct, yes.
There's
but
only
it's,
one way to choose nothing.
yeah, there's only one way to choose nothing. You don't do anything, but you don't. There's only one way to choose nothing, just do nothing. So this is the difference between permutations and combinations. Now, let's go to, again, my example, but now I'm not going to have pennants. I'm going to have the letters A, B, C, and D. Let's use only two symbols, zeros and ones, to make it more computer scientific. Well, I guess now all of you have taken advanced classes. So we can, you typically have, you can give answers to all of those examples that I'm saying. But how many words can we create of length 6, arrays of length 6? Of 6, how do we call this, bits? The 0 or the 1 bit? It's a bit. Byte or a bit? 0, 1 is a bit. Yeah, I'm always getting confused. Did I write it? I think it's with a Y, okay, correct? B-I-T, bit, yes. Because this is the byte, huh? Don't byte.
Well, byte is B-I-T.
Yeah, B-Y. No, but dogs bite with I. So how many arrays of 6 bits by using zeros or ones can we form? Since I'm giving you 6 positions and only 2 symbols, you understand that you have to use them with replacement. You can use as many times as you want the 0, as many times as you want the 1. So how many of those can we form? Of course, in the array, every position counts, okay? It matters which is first, which is second, as you read from the left. So how many choices do we have for the first position? 2. And of course, since we are not restricted, and the zeros and the ones, we have 2 more for the second, 2 for the third, and so forth and so on. So that gives you 2 to the 6th power, which is exactly an easy application of this rule. For the first position you have 2 outcomes. For the second position you have 2 more outcomes. And for the third 2 more. And that gives you the multiplication 2 with itself 6 times, which gives you 2 to the 6th. So what are these? These are ordered selections with replacement. Of R items from a pool of N items. M distinguishable items. So these are can be done in N to the R ways, okay? And in my example, R was equal to 6 because I wanted an array of 6. I want to pick R items from a pool of 2 items. N was equal to 2. Okay, and that gave you this rule. As you know. So these are the rules of counting I want to focus on. And I don't want us to learn anything more. That's simple, and we can stay there. You can stay with this, okay? So let's do some problems. Now, we will begin calculating probabilities. And to begin calculating probabilities, we will use the so-called classical probability model. Now, when we calculate probabilities, unless we're given a probability model, which is what we will be doing very soon when we'll start using the concept of random variables, where the probability model is given to us or it can be derived from a certain set of rules. When we don't have anything to work with, no hint about the probability model, we can always assume that we are in the classical regime, and the classical probability model is encapsulated in one principle. That's the model that was introduced by Blaise Pascal. All simple events have the same probability. So if we have n simple events in an experiment, then each one has probability 1 over n. One over n. Okay? Is it clear? Now, the probability, when we want to calculate the probability of A, then we have to look at the description of A. And accordingly to the classical probability model, this is going to be the following ratio. The denominator is the number of all simple events, of all possible simple events in the experiment. The numerator is the number of all favorable events, favorable simple events. And by a favorable simple event, I mean one of the events that fit in the description, one of the simple events, each one of the simple events that fits in the description of the event A. Okay? So now this has to become a little bit more clear. So let's clarify that. Let's understand how many simple events and how many favorable events. Let's learn to count. So let's look at the lottery. Let's look at the slope. Okay, let's see the lottery. Mega Millions. I think it's how to play, probably what we want. So, players may pick 6 numbers from 2 separate pools of numbers. 5 different numbers from 1 to 56, and 1 number from 1 to 46. Let's forget what the easy pick is, or select easy pick, which is a pseudo-random. It's a pseudo-random number generator, but I suspect it's not very pseudo-random. I think it gets a seed, which is random, so that's the first number, and then here's an algorithm which numbers it gives you. but I have not been able to confirm that because I have to, but I suspect that might be the case. Anyway, let's see what are the possible cases. The odds for winning. So you select 5 different numbers from 1 to 56. So the only thing you want to do is to pick the numbers, the correct numbers, from 1 to 56 if you want to win the lottery, all the 6 numbers right. So let's think about the first part. So Texas Lottery. So select 5 numbers from 1 through 56. Okay? Does it matter in which order you have selected the numbers? No. What matters is whether you have selected the 5 numbers correctly. You have guessed the 5 numbers correctly. You don't have to match the order in which they appear when they come out from the hopper. So what is your selection? Order or unordered? Unordered, why? Why order? Now you select, you have to guess the right numbers from 1 through 56. Let's say that you have only 3. Let's say that you have only 3 numbers. It's not 5 numbers. Let's say that you have 3 numbers. And the numbers, I'm the hopper and I'm declaring those numbers. 3, 15, and 55. If you have a ticket where in the 3 positions you have 15, 3, and 55, 3, and 15, you match the numbers. Correctly? Correct? Am I right? By the rules of the lottery. So does the order matter or not? It does not matter. The only thing that you need to have is the correct group of numbers, the correct group of 5 numbers. They don't have to be in the same order in which they come out from the hopper, but they have to match the 5 numbers of the hopper. They have to be exactly the same group. So those numbers, so winning numbers are selected okay, then you select the numbers from 1 through 56. Do you select the same numbers? Hmm? Well, let's look at the lottery. How to play. 5 different numbers. So what does that mean?
It's not the same.
Not the same. So is it with replacement or without replacement? It's without replacement. Okay. So and it's that because when the hopper draws the numbers, they will draw 5 different balls. So there will be the numbers will destined to be different. So they're going to give you to allow you to have typically non-winning selections selected without replacement per the rules of the lottery, and the order doesn't matter. The order does not matter. So what do we have? What are these 5 numbers out of the 56? How do we call them? How did we call them? Those are combinations. Okay, so essentially what we do in the first part of the lottery is combinations of 5 numbers out of 56. So That portion is combinations. 56, choose 5. Now the lottery has a second part, which is called the Powerball. And you have, that number is from 1 to 46. So how many choices do you have for this number? 46, correct? So to win the lottery, to win the jackpot, you have to select all those 6 numbers, the 5 from 1 through 56 and the 1 from 1 to 46 correctly. To win the jackpot, to win the first prize. So, and 46 choices for the Powerball. So the jackpot consists of choosing correctly, guessing correctly actually, the 5 winning numbers. And the Powerball. So experiment 1 is to choose the 5 winning numbers correctly. This is experiment 1. Experiment 2 is to choose the Powerball. So how many outcomes do we have? 56 choose 5 combinations times 46 possible choices. So those are this is the total number of simple events. What is the probability of winning the jackpot? Yes, all the 6 numbers correct. 1. So the probability for the jackpot in the Texas Mega Millions is 1 over 5. You do the math and you find the odds. That's a small number. Okay? Why do they put the Powerball? Suppose that they were, what's the Powerball? The Powerball is the 6th column. Suppose that they had 6 columns with 56 numbers. You had to guess 6 numbers, correct? What that probability would be equal? The probability of winning. We have our own modified lottery, so we can understand why they use the Powerball. It would be 1 over 56 to 6, okay? So with 6 balls, probability of winning with 6, guessing correctly the 6 numbers, 6 numbers from 1 through 56 would be 1 over 6 different numbers, 56 to 6. So which is bigger probability? This one or this one? What do you think? Okay, let's see why is the bottom one. We have to compare. What do we have to compare? What would make this to be a bigger probability? 56 to 6 should be smaller than 46. 56 choose 5. Okay, let's see if this inequality is true. Well, the left-hand side is 56 factorial, 6 factorial by times 50 factorial. The other one is 46, 56 factorial, 51 factorial times 5 factorial. Well, there are some simplifications that they can be made very quickly. We can also do some here in the denominator, or just bring this denominator up. So we have 51 factorial times 5 factorial divided by 6 factorial times 50 factorial. Less than 46. Let's see if this inequality is valid. Let's simplify a bit more. 55 divided 51 divided by 6 less than 46, which is valid. So this is true. Correct? That's why they put the Powerball, because technically they reduce significantly the odds of winning. Look how much smaller this number is compared to this number. This number is roughly 7, and this is 46. Your odds of winning have gone down by a factor of 6, roughly.
And that's because it's a set.
It's a unique selection, yes. You see, the two portions, what they do is that they create essentially an ordered selection. The first 5 and the second portion, which is the Powerball. You multiply them. Whereas here, if all the 6 columns were put the same, since the order they were put and they had the same significance, the selection would be unordered. So it would favor you more. Although instead of, for the 6 column, instead of using 46, I used 56 numbers. I use the same bigger. Still, the odds are not favoring you with the Powerball, but they are favoring you with the other system. That's why they put this Powerball there. So, what is the probability of winning, but not with the Powerball? Winning the 5 numbers right, but not the Powerball. I'm advancing a little bit the. So what is you guess the 5 numbers right, but not necessarily the Powerball? What could be this probability? What's the number of favorable outcomes?
Just use the combination algorithm, so it'd be 56 factorial over 5 factorial.
So we use, the first part is to guess correctly the 5 numbers, okay? How about the Powerball? It doesn't matter. So how many favorable outcomes do we have? Why 46? You win only the 5 numbers, not the Powerball, 45. Okay? Win, guess correctly the 5 numbers, guess correctly only the 5 numbers, and not the Powerball. Okay, this means that you guess correctly the first part. That can be done only in one way because it consists of 5 numbers. You have to guess correctly all of them, but you don't pick the Powerball correctly, so you have 45 choices out of the 46. The 46th is the correct one, but we said you missed it. So the number of the favorable events, so this probability of this event would be 45 divided by what we had before, 46 times 56, choose 5. The probability of this. Is it clear? Now, there is one very important suggestion. I want to give you a tip here. It's very important the way you count the numbers, the rules that you set to define the simple events for the denominator have to be applied the same way for judging the favorable simple events for the numerator. You can have a different definition for the simple events for the denominator of this fraction and a different way for the simple events of the numerator, because then you divide unequal quantities. The rules should be kept the same. Now, start always, when you do a problem, start always with the denominator of the fraction. It's easier and it's a good warm-up, and it gives you some insight about the problem. Sometimes it's more difficult to calculate the numerator, because you have to understand exactly what the favorable event is. To understand the simple events is technically easier than to understand the favorable simple events. All right? Let's do another problem. Well, let's say that this classroom this class has 20 students. I want to divide you into two groups. How many ways can I do that? In two groups. Correct question, very good. Of equal size. In how many ways can I do this? I have 20. Let's say that you're 20 here. I don't think you are. But let's say that you're 20. And I want to divide you in two groups of equal size. So each group should have 10 students. How should I do it? How many ways can I do it?
It's another combination method. So
Why is it combination?
because it doesn't matter what order you pick the people in.
What order I pick the people in?
Doesn't matter.
No, it doesn't matter. What does it matter?
Just so they're not in group 1 or group 2.
What matters is the group affiliation, correct? So it's like assigning a flag or a predicate, okay? I group you, I put you in a category. I do assign a class. So here we have an unordered selection, so the selection is unordered. Because what is important is the membership. Do we do it with replacement or not? Membership to a group. Okay, selection is done without replacement. Because you cannot assign the same student into groups. So we have combinations of 10 students out of 20, which can be done in 20 to 10 ways. Okay, because that's the number of combinations. Is it clear? So let's look at the book. Let me give me a second just to open the book. I think it's the other one. I don't know why it's not giving it to me. And let's work on some problems. Let's look at problem 30. A friend of mine is giving a dinner party. You can read it if actually I can enlarge it a little bit so you can read it. Who is going to help me with the reading? That's fine. Basic rules of confining. That's what the handwritten recognition picked. Who wants to read the problem? Who wants to volunteer a strong voice? Thanks. Yes.
A friend of mine is giving a dinner party. His current wine supply includes 8 bottles of Zinfandel, 10 of Merlot, and 12 of Cabernet. He only drinks red wine, all from different wineries. Do I read all the choices?
Let's read choice A, and let's talk about A.
A, if he wants to serve 3 bottles of Zinfandel and the serving order is important, how many ways are there? First question.
Mm-hmm. So the bottles are from different wineries, okay? And what it says is all from different wineries. So what do we understand from this statement? All bottles are from different wineries. That the bottles are distinct, although they may all be Zinfandels or something, those are distinct items. So we have 3 bottles of Zinfandel and serving order is not important. So what are those 3 bottles are going to be? And serving order is important. Okay. Okay. How did I? Yeah. All right. Sorry. I'm making up. Thanks for correcting. Order is important. So here we have what? An order selection.
Permutation.
It's a permutation. What else do we need for the permutation? Just the permutation, replacement. So do we pick them with replacement or not? So we pick them without replacement. We pick those bottles without replacement. So how many bottles of Zinfandel do we have in total? So we have the pool of items is 8 distinct items, correct? So we pick, the order is important, we pick 3 out of them. So in how many ways can this be done? So we have 8. Actually, there are several ways you can remember this. This is n is equal to 8, r is equal to 3. And what is the rule that we have used? We have mentioned that we need to use here. It's this one. It's a permutation of 3 items out of a pool of 8 distinct items. That's why we spoke about the labels. So this can be done in how many ways? Can be done in 8 factorial divided by 8 minus 3 factorial. So this is 8 factorial over 5 factorial. So it is how many ways? 6 times 7 times 8. Whatever this number is. Okay, because we have permutations. But you have to go through the checklist. Is the selection order or unordered? Is the selection with replacement or without replacement? And then you give the answer. Okay, I want to see this all this when you solve problems. All right? Is it clear? Don't just give me this. Don't do that. That's not going to give you any points. I want to see how you arrived into that number. The rationale. And of course, if you put the bottles are distinct items because all the labels are different, that's very important. That gives you extra points. Am I clear enough? All the way? Okay, thanks. Okay, let's look at another problem now that we have the book. Any question?
Can you write the answer the way you want to see it?
Essentially, I spoke the answer in the recording, which it's going on. So you understand now. I mean, I don't have to write something.
But if you said there are 8 items that you failed to mention,
Let's.
would you get these off?
Yes.
Okay. You have to say the
You get points off for everything. Period.
Great answer. Points up.
So it has to be the very right answer, not just the right answer. The very right answer. And of course, if you give, look how it works. Let's resume. Let's do question B. If 6 bottles of wine are to be randomly selected from the 30 for serving, in how many ways can we do this? Randomly selected. Do we care here about the order? No, it doesn't say. Just pick a group of 6. So here, the order does not matter for question B. So here for question B, the order does not matter. Because the problem says just pick 6 bottles. What does the randomly imply? Besides that, it's not biased. I mean, all bottles are equally likely to be picked, okay? All bottles are equally likely to be picked. Do we pick them with replacement? No. You pick the bottle, you can't pick it twice. We pick them without replacement, or they are picked without replacement. So we form combinations. That's how you should write. That's the best. You can't do better than that. You have to have a degree in creative writing to do better than that. So, combinations of 6 items out of 30. 6 items out of 30 distinct items, which can be done in 36 ways. Okay? Let's do another problem before let's need to leave the classroom. Let's do problem 35, which is here on the screen. Can you all read it? Let's read question A. The production facility has 20 workers in the day shift, 15 in the swing shift, and 10 workers in the graveyard shift. And they have a quality control consultant who's going to select 6 workers for an in-depth interview. Suppose the selection is made in such a way that any particular group of 6 workers has the same chance of being selected as does any other group. How many selections result in all 6 workers coming from the day shift? So essentially, what is the probability that all 6 are selected from the day shift? How many do we have in the day shift? We have 20, okay? So what do we have? What do we form when we select those workers? Those 6 workers, what do we form? We form combinations. Why? Because once you selected them, you are not going to reselect them. So you select them without replacement. Does the order matter? No. It's just what matters which individuals you have. Because you're only going to interview them. You don't interview the order of the interview. The order in which they will be interviewed does not make any difference here. That's something we can understand easily. So we have combinations. So we have that can be done in how many ways? 20, choose 6. Okay? Now, let's look at the last question, D. What is the probability that at least one of the shifts will be unrepresented in the sample of workers? Yes.
So when it asks how many, what's the odds of selecting all from the day shift, do we do 20 and choose 6 over 45?
Oh, the probability. We didn't do the probability. I did only the selections. What is the probability that all 6 workers will be from the day shift? Okay. We form selections of workers, okay? And I violate my own rules here, evidently. What are all possible simple outcomes? What are the simple outcomes here in this experiment? What are the simple outcomes? Describe them to me. Selections of 6 workers for the interview, okay? Which can come from any shift. So how many workers do we have? 20 plus 15 plus 10, we have 45, a total of 45. And we select 6. So we select combinations for the reasons we have explained. So all simple events are 45 to 6. So these are all, this is the number of all simple events. Now, the favorable event is that all workers are selected from the day shift. All 6 are selected from the day shift. So what does that mean? It means that how many ways can be done? 20 workers are in the day shift, so it's 20 to 6. So the probability that all 6 are selected from the day shift is 20 to 6 divided by 45 to 6. You need not do any further calculation. That's the number I want you to do. That's the result I want to see. Don't calculate this number because it's going to be useless. I'm not going to use a calculator. I don't know how. Okay, let's look. Do you have a little bit more time? Because there's no class following us here, trailing us. So we can use the classroom for a little bit longer. You want to do one more question? Okay, let's do a more challenging question. Now, I don't want to keep you for longer, so whoever feels that you don't want to, you have somewhere to go, you can go. This is going to be part of the video. So let's do question C. What is the probability that at least 2 different shifts will be represented among the selected workers? What is the probability that at least 2 different shifts will be represented among the selected workers? At least 2. Sometimes when we have these statements, at least or at most, it's very useful to switch to the complementary event. So let's say the event A is at least 2 shifts are represented in the group. The group that will be in there. The complementary event is what? What's the description of the complementary event? A prime.
Only one shift.
At most 1 shift. Since you are going to pick workers that will come from a shift, that means exactly 1 shift is represented in the group. Okay? So it's easier to calculate the probability of A prime, because if we calculate the probability of A prime, what do we know? We know that the probability of A prime plus the probability of A is equal to what? What the sum is equal to? It's equal to 1. So if you calculate this probability, then you can calculate this probability. All right, so let's go for the probability of A prime. We want to calculate the probability of A prime. How do we do that? Exactly 1 shift is represented in the group. How many shifts do we have? 3. The morning, the swing, and the graveyard. So that group can be either all from the morning, or from the swing, or from the graveyard. Okay? So this breaks down to the following. All 6 come from day. You see how I put it schematically inside the parentheses where I put the probability? Swing or graveyard. So those are 3 sub-events. So A prime can be realized if one of these sub-events becomes realizable. What are these 3 sub-events? Are they exclusive or not? If a worker belongs to 1 shift, because the shifts are non-overlapping hours or non-overlapping time segments, a worker cannot be in both shifts, okay? So those are exclusive events. So since those are exclusive events, I can add their probabilities. So P of A prime is the sum of all 6 come from the day shift, plus all 6 come from the swing shift, plus all 6 come from the graveyard. So I added the probabilities because these 3 events, these here, are all exclusive, mutually exclusive as we say. So the probability of all of them gives the probability of A prime. The sum of these probabilities gives the probability of A prime. So what's the probability of the first one? We just calculated it. It's this. So the probability of the first one is 20 to 6 divided by 45 to 6. What about the probability of the second one? Well, let's look at the problem. The problem says that there are 15 workers on the swing shift and 10 workers in the graveyard shift. So therefore, the second term has probability 15 to 6 divided by 45 to 6, and the third has 10 to 6 divided by 45 to 6. And the result, let's just group all of these things together. That's the end of the story. Okay? Any questions? What?
Technically, since we solved for A prime, that's not it. So,
Well, technically, then you calculate this result. This is the probability of A prime. Then you subtract this probability. Now we're going to do problem 36. So we have an academic department with 5 faculty members. And the department narrowed its choice for department head to either candidate A or candidate B. Each member then voted on a slip of paper for one of the two candidates. Suppose that there are actually 3 votes for A and 2 votes for B. If the slips are selected for tallying in a random order, what is the probability that A remains ahead of B throughout the vote count? Now, this event would occur if the selected ordering would be the way it is, for example, like this, AA, B, AB, and not A, B, B, A, A. So this is a rather, this is a problem which is not very easy. Let's understand what are the simple events here. So we have 5 people who will turn in their votes, and their votes will look like, so that's problem 36 here, like this. Let's say these are the ballots, and you will have these ballots when you count them. They will look like that. So this is one simple event. So how can we understand what is the way to codify these simple events? Well, since they have to vote for A or B, they pick symbols A or B with replacement, because more than one person can vote for the same candidate, so they pick with replacement. And the votes, since each one votes for one person, are distinct. So votes are or tally results because that's what we're interested in, can be thought of as words with A's or B's and length 5. Like the one that I have here. So this tallying result would correspond to A, B, A, B. So these kinds of words. So how many of those can we form? So we pick symbols with replacement, but the order does matter. Let's solve the problem by thinking in the following way. Let's say we have 5 positions. Position 1, 2, 3, 4, 5. Those positions will be grouped. And what I'm trying right now to find is how many words like this can I form? Words of length 5 with A's and B's. And by the way, we need words of 5 letters with 3 A's and 2 B's, because that's what the problem specified. 3 voted for A and 2 voted for B. So we have to find which positions, which of the 3, 4, 5 positions here will put the A. Once we decide those positions, then automatically the remaining positions will be occupied by B. So here, in that example that I'm having here, the positions are first, second, and fourth for A. So in how many ways can I select those positions out of the 5 positions? The order in which they appear, it doesn't matter what appears, which positions will belong to the group. And once you select a position to place the A, you don't reselect that position again, because that will be occupied by A and not by B. So we select those positions, select 3 positions out of the 5 to place A. The remaining 2 positions will be selected for B. Order does not matter. So this can be done in 5, choose 3 ways. So the number of all simple outcomes, and simple outcomes are exactly these words of length 5 with 3 A's and 2 B's, is 5, choose 3. Now we have to find the number of favorable events. Now, what is a favorable event? A favorable event is the arrangement, the word, where the number of A's before the number of A's the problem says, suppose that there are actually, if this, what is the probability that A remains ahead of B throughout the vote count? So whenever we actually, that amounts to, whenever we have arrived at the position, let's say at the 4th position or the kth position, and this k is between 1 through 5, A has more votes than B. So we see more A's up to the kth position than B, and this is true for all A 1 through 4. Because automatically when we reach 5, we see we have 3 A's and 2 B's, that's automatic. No, even up to 5. Yes, because we can have A, B. Yeah. So from positions 1 through 5, all the A's should supersede the number of B's that we have. Therefore, the 5th position, that will happen anyway. So how that can be done? First position, the first vote in the tally. It has to be an A, because if the first vote is a B, then B is ahead in the count. Second position. The second position must also be an A, because if it were a B, then A and B would have had exactly the same votes, would be sharing the votes up to the second vote, so A is not ahead in the vote count. The third vote can be an A or a B. So for the first and the second position, we have locked to both A's, the first and the second vote, but when the third vote has been drawn for the tallying, that can be either one. So we have two choices, either A or B. So two choices here for the third vote. Let's go to the fourth vote. If the third vote was an A, then automatically the fourth and the fifth are B's. If the fifth vote is a B, if the third vote is a B, then the fourth vote has to be an A. So depending, and that would basically close the result. So the favorable results will be A, B, B, A, B, and then automatically we must have an A. And of course the fifth position, the fifth vote would be a B. So we're done with the choices, all the choices from up to the third vote. And do we have any other votes here? No, we don't have any other votes. So essentially we have two choices, two favorable events. So now that's easy to calculate the probability that A stays ahead in the vote when it's receiving 3 votes versus B who's receiving 2 votes. And that concludes today's lecture.